There's a boundary around you right now that you cannot see, cannot touch, and cannot measure with your hands. It stretches across billions of miles of empty space, invisible to every instrument we've ever built, and yet it might be the most important wall humanity will ever face. Not because it keeps us in, but because crossing it requires something we may never possess: the ability to move beyond the fundamental limits written into the structure of reality itself. We are surrounded by space that appears infinite, and yet we are trapped. Not by lack of ambition, not by politics or funding, but by physics, by time, by the universe's refusal to bend its rules for a species that dreams of reaching the stars. We have sent machines to the edge of our solar system. We have photographed distant galaxies. We have walked on another world. And yet, when we look outward at the true scale of what lies beyond our sun's influence, we are forced to confront a possibility that science fiction has spent a century helping us avoid: that we are a solar system-bound species, that the distance between stars is not just large, but impossibly, prohibitively, permanently large, that the universe has built walls out of distance itself, and no amount of engineering will ever bring them down. This is not a story about pessimism, it's a story about scale, about what happens when you take the numbers seriously, about what the universe actually is, rather than what we imagine it to be, and about the quiet, unsettling realization that humanity's future might be measured not in light years, but in astronomical units. Not across the galaxy, but within the sphere of influence of a single, unremarkable star. Let's begin with the boundary itself, because before we can understand why we can never leave, we first need to understand what leaving even means. When we talk about the solar system, we're not talking about the 8 planets. We're not even talking about the orbit of Neptune, 2.8 billion miles from the Sun, where sunlight takes more than 4 hours to arrive. The solar system is vastly larger than the neat diagrams in textbooks suggest. It extends outward in shells, layers of influence that grow progressively weaker but never quite disappear. The first real boundary is the heliopause, the point where the solar wind, the stream of charged particles flowing outward from the Sun, finally meets the pressure of interstellar space and stops. The Voyager 1 spacecraft crossed this boundary in 2012, about 11.7 billion miles from Earth, becoming the first human-made object to enter interstellar space. It took 35 years to get there, traveling faster than any spacecraft designed before it. But the heliopause is not the edge of the solar system. Beyond it lies the Oort Cloud, a vast spherical shell of icy objects loosely bound by the Sun's gravity. It begins somewhere around 2,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. 2,000 astronomical units is 186 billion miles, a distance so large it becomes difficult to hold in your mind as a real, measurable thing. The outer edge of the Oort cloud extends perhaps 100,000 astronomical units outward, nearly halfway to the nearest star. This is the true edge of the Sun's gravitational influence, the point at which an object no longer orbits our star, but drifts free into the galaxy. Voyager 1, moving at 38,000 miles per hour, will not reach the inner edge of the Oort cloud for another 300 years. It will not clear the outer edge for 30,000 years. By then, its cameras will be silent, its transmitters long dead, its plutonium power source decayed into stillness. It will drift through the dark, a monument to a species that built it, launched it, and then lost the ability to hear it answer back. And Voyager 1 is traveling in a straight line, without stopping, without slowing down, through a region of space that is essentially empty. Imagine now what it would take not just to pass through, but to carry a crew, to slow down at the destination, to bring along everything a human being needs to survive, to return. The heliopause is not a wall. The Oort Cloud is not a wall, but the distance itself is. The nearest star beyond our own is Proxima Centauri, a small red dwarf 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at 186,282 miles per second, the fastest speed anything in the universe can move. Light from Proxima Centauri, racing across the void at this unimaginable speed, takes 4 years and 3 months to reach Earth. That distance, expressed in miles, is 24.9 trillion. It is a number so large it loses meaning. You cannot picture it. You cannot drive it. You cannot count it. You can only calculate it and hope the magnitude of what it represents eventually settles into understanding. Voyager 1, moving at 38,000 miles per hour, will take 73,000 years to travel the distance to Proxima Centauri if it were aimed in that direction. It is not. It is aimed at a star called AC plus 79 3888, which it will reach in 40,000 years, passing within 1.6 light-years. But these numbers, already incomprehensible, are only the beginning of the problem, because Voyager is not slowing down. It is not carrying humans. It is a 1,500-pound machine with no life support, no radiation shielding for biology, no fuel reserves. It is the fastest object humanity has ever sent into space, and it is still laughably, impossibly slow. Let's try to understand the scale more intuitively. If the Sun were the size of a basketball, the Earth would be a peppercorn orbiting 26 feet away. Neptune would be 800 feet away. The heliopause, where Voyager crossed into interstellar space, would be half a mile distant. And Proxima Centauri, the nearest star, would be 4,000 miles away. In this scale model, the fastest spacecraft we've ever built is moving at 0.6 miles per hour. Would take 500 years to cross the distance between the basketball sun and the nearest other star at this scale. The universe is not empty space waiting to be filled. It is distance, enforced by physics, stretched across gulfs that make human timescales irrelevant. But perhaps we could go faster. Perhaps with better rockets, better fuel, better engineering, we could cut the travel time from tens of thousands of years to hundreds, to decades. Perhaps we could reach 1/10 of the speed of light, a speed that would allow a spacecraft to reach Proxima Centauri in 42 years. Surely that is within reach. Surely we could build something that fast. Here is where the second wall appears: energy. Every object in motion carries kinetic energy, the energy of movement. The faster something moves, the more energy it carries, and the energy scales not linearly, but exponentially. To double your speed, you need 4 times the energy. To triple it, you need 9 times. To accelerate a spacecraft to 1/10 of the speed of light requires energy that is difficult to comprehend. Let's make it tangible. Imagine a spacecraft weighing 1,000 tons, roughly the mass of the International Space Station. To accelerate this craft to 10% of light speed, you would need approximately 450 trillion megajoules of energy. For comparison, the entire electrical output of the United States in a year is about 4 trillion megajoules. You would need more than 100 years of America's total energy production just to accelerate a single spacecraft to that speed. And this is only the kinetic energy of the final velocity. It does not include the energy lost to inefficiency, to heat, to the process of actually generating thrust. Real-world rockets operate at efficiencies far below 100%. Chemical rockets, the kind we use now, are about 60% efficient at converting fuel energy into motion. Even the most optimistic advanced propulsion concepts struggle to reach 90%, and you would need to do this twice. Once to speed up, once to slow down. Otherwise, your spacecraft arrives at Proxima Centauri at 10% of light speed and continues into the void, unable to stop, unable to explore, a tomb hurtling through eternity. The deceleration problem is often ignored in discussions of interstellar travel, but it is just as difficult as acceleration. You cannot use air resistance to slow down because there is no air. You cannot use parachutes or friction. You must carry enough fuel to fire your engines in reverse, generating thrust opposite to your direction of travel, bleeding off velocity over months or years until you are slow enough to enter orbit around your destination. This means you must carry twice the fuel or close to it. And fuel has mass. Mass requires energy to accelerate. The equation spirals outward, each solution creating new problems. But let's assume you solve the energy problem. Let's assume you have fusion reactors, antimatter engines, some propulsion technology that extracts energy directly from the vacuum of space. You still face the rocket equation, one of the most unforgiving laws in physics. The rocket equation states that the final velocity of a spacecraft is determined by the exhaust velocity of its engine and the natural logarithm of its mass ratio, the total mass at launch divided by the final mass after all fuel is burned. To go faster, you need either a more efficient engine or more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that fuel. The relationship is exponential in the wrong direction. For a chemical rocket to reach just 1% of light speed, the mass ratio would need to be in the millions. You would need a fuel tank the size of a mountain to push a payload the size of a car. Advanced propulsion helps. Ion drives, nuclear pulse propulsion, fusion rockets. All of these offer higher exhaust velocities which reduce the mass ratio, but they still cannot escape the fundamental equation. Every gram of spacecraft, every ounce of structure, every human being, and every supply they need for the journey adds mass. And mass is the enemy of speed when you're confined to carrying your own fuel. Consider nuclear pulse propulsion, the Orion concept developed in the 1950s. The idea was to detonate nuclear bombs behind a spacecraft, using the explosion to push it forward. Each detonation would provide a burst of thrust, and by stacking thousands of bombs, you could theoretically reach a few percent of light speed. The engineering challenges were enormous. You would need a massive shock absorber to protect the crew from each blast. You would need a pusher plate capable of withstanding thousands of nuclear detonations without melting or fracturing. You would need to carry thousands of nuclear weapons, each adding mass to a system already struggling with the rocket equation. And even if you solved all of this, even if you built an Orion ship and launched it toward Proxima Centauri, the journey would still take more than a century. The crew would still die in transit, and you would have irradiated your launch site with fallout from the initial detonations. Nuclear pulse propulsion is not politically viable, not environmentally responsible, and not physically capable of solving the interstellar travel problem. It is a marginal improvement over chemical rockets, nothing more. Fusion propulsion offers better performance. A fusion rocket could theoretically reach 10 to 15% of light speed by fusing hydrogen into helium and expelling the products at relativistic velocities. The fuel is abundant. The energy density is enormous. The exhaust velocity is high enough to make interstellar travel conceivable, if not practical, but we do not have fusion propulsion. We have not yet achieved sustained fusion reactions that produce more energy than they consume. The ITER project, the International Fusion Research Reactor under construction in France, aims to achieve net positive fusion by the 2030s. But ITER is not a rocket. It is a stationary reactor designed to heat plasma to 150 million degrees Celsius using powerful magnetic fields. Miniaturizing this technology, making it light enough and efficient enough to propel a spacecraft, is a problem that may take another century to solve, if it can be solved at all. And even fusion propulsion does not eliminate the rocket equation. It improves it. It makes the mass ratio more favorable. But it does not allow you to carry infinite fuel. It does not allow you to accelerate indefinitely. You are still constrained by the amount of fuel you can carry and the efficiency with which you can convert that fuel into thrust. You might propose a solution, a light sail, a spacecraft pushed not by onboard fuel, but by a laser fired from Earth or from a station in orbit. The laser strikes an enormous reflective sail, transferring momentum, accelerating the craft without carrying fuel at all. The Breakthrough Starshot initiative has proposed exactly this. A fleet of tiny gram-scale probes accelerated to 20% of light speed by ground-based lasers, reaching Proxima Centauri in 20 years. It is an elegant idea. It is also not a solution for human spaceflight. The sail required to accelerate a human-carrying spacecraft would need to be hundreds of miles across. The laser would need to be powerful enough to ionize the atmosphere, to boil the air itself. You would need to fire this laser continuously for months, tracking the spacecraft as it accelerates, maintaining perfect alignment across millions of miles. And once the craft is underway, it cannot slow down. There is no laser at Proxima Centauri to fire back and decelerate the ship. It would arrive and pass through, a flyby mission only, unable to stop, unable to study, unable to return. Some have proposed using a magnetic sail to slow down, a device that generates a magnetic field and uses it to interact with the interstellar medium, the thin gas between stars. The drag from this interaction would gradually reduce velocity over years or decades. But the interstellar medium is extraordinarily thin, about 1 atom per cubic centimetre. The deceleration would be minimal. You would need a magnetic field hundreds of kilometres across, sustained by power systems that function perfectly after decades in transit, to slow a spacecraft moving at a significant fraction of light speed. And even then, you might not slow down enough. You might still be moving too fast to enter orbit, too fast to deploy instruments, too fast to do anything except continue into the void. And even if you could stop, even if you could somehow slow down using magnetic fields or another mechanism, you would still be stranded. Because the laser only pushes outward, there is no way back. A light sail mission is a one-way trip, and not just for the spacecraft. It is a one-way trip for the information it gathers, for the images it transmits, for any discovery it makes. The signal takes years to return. The lag between question and answer grows with every mile travelled. You send instructions to adjust course, and by the time they arrive, the spacecraft has already passed the point where the adjustment would have mattered. This is the energy wall. It is not built from steel or stone. It is built from the mass-energy equivalence, from the tyranny of the rocket equation, from the fact that energy is not free and propulsion is not magic. Every second of thrust, every increment of speed, every gram of payload costs energy, and the energy requirements grow faster than the solutions we can build. But perhaps energy is solvable. Perhaps in a century or 5 centuries, we will have reactors that make energy cheap and abundant. Perhaps we will mine asteroids for fuel, build particle accelerators in space, harness the sun's entire output with a Dyson swarm. Let's assume we solve energy, we still face the speed of light. Einstein's theory of special relativity tells us that the speed of light, 186,282 miles per second, is not merely fast. It is the maximum speed at which anything in the universe can travel. Not because we haven't built a fast enough engine, but because space-time itself forbids it. As an object with mass approaches the speed of light, its relativistic mass increases. It becomes harder and harder to accelerate. To reach the speed of light would require infinite energy, not a large amount of energy, not an impractical amount, infinite energy, a physical impossibility. The speed of light is not a barrier in the sense of a wall you could break through with enough force. It is a limit written into the structure of reality. The mathematics of special relativity are precise and unyielding. The Lorentz factor, the term that describes how time, length, and mass change as you approach light speed, grows without bound as velocity approaches c, the speed of light. At 90% of light speed, the Lorentz factor is 2.29. Time slows down by this factor, lengths contract, and the effective mass of the spacecraft increases. At 99% of light speed, the factor is 7.09. At 99.9%, it is 22.4. At 99.99%, it is 70.7. The curve is asymptotic. It shoots upward toward infinity, and there is no amount of thrust, no amount of energy that can push past it. Even if you could somehow reach 99% of light speed, the journey to Proxima Centauri would still take more than 4 years as measured from Earth. And from the perspective of the travelers, time dilation would compress that experience, making the journey feel shorter. At 99% of light speed, the trip might feel like 6 months to the crew. But that is not the same as making the distance shorter. The universe does not care about subjective time. The energy required, the radiation encountered, the engineering, challenges, all of these remain. And when the crew returns, if they return, they will find that decades have passed on Earth. Their friends and family will be older or dead. The society they left will have changed. They will be travelers not just through space, but through time, disconnected from the world they came from by the relativistic effects of their journey. This is the twin paradox made real. The astronauts age more slowly than those who stay behind, a consequence of special relativity that has been confirmed experimentally with atomic clocks on airplanes and satellites. At relativistic speeds, the effect becomes extreme. A crew that experiences a few years in transit returns to find that centuries have passed on Earth. They are exiles in time, unable to rejoin the world they knew, forever displaced by the physics of their journey. And Proxima Centauri is the nearest star. The next nearest, Barnard's star, is 6 light-years away. Sirius is 8.6 light-years. The stars in our immediate neighborhood, the ones we could hypothetically reach within a human lifetime, traveling at relativistic speeds, number fewer than 20. Beyond that, the distances stretch into dozens, then hundreds, then thousands of light-years. The galaxy is 100,000 light-years across. A spacecraft traveling at the speed of light would take 100,000 years to cross it, and that is assuming it never stops, never slows down, never deviates from a perfect straight line. We live in a universe where the distances are measured in the time it takes light to travel, and light itself is too slow. But it is not only distance and energy, it is also the space between. Interstellar space is not empty. It is filled with gas, dust, radiation, and high-energy particles moving at relativistic speeds. The density is low, about 1 atom per cubic centimetre, but at high velocities, even a single atom becomes a threat. At 10% of light speed, a collision with a hydrogen atom releases energy equivalent to a high-velocity rifle bullet. A dust grain the size of a sand particle releases energy equivalent to a hand grenade. A pebble-sized object releases energy equivalent to a small nuclear weapon. A spacecraft traveling at these speeds would need shielding, not from weapons, but from the interstellar medium itself. Shielding means mass. Mass means energy. Energy means time. The problem is not just stopping the particles, but dissipating the energy they carry. When a high-velocity particle strikes a shield, it does not simply bounce off. It transfers its kinetic energy into the material, heating it, vaporizing it, creating secondary radiation that can be just as dangerous as the original impact. You could build a thick shield, meters of solid material designed to absorb impacts, but thick shields are heavy. You could build a magnetic shield using powerful magnetic fields to deflect charged particles before they reach the hull, but magnetic fields require power constantly for the entire journey, and they only work on charged particles. Neutral atoms, dust grains, and photons pass through magnetic fields unaffected. Some have proposed using a cloud of gas or plasma ahead of the spacecraft, a sacrificial buffer that absorbs impacts before they reach the ship. But maintaining this cloud requires mass. You must carry the gas with you or harvest it from the interstellar medium as you go, and harvesting requires energy and time and mechanisms that add complexity and failure points to an already impossibly complex system. And then there is radiation. Space is bathed in cosmic rays, high-energy particles accelerated by supernovae, neutron stars, black holes. On Earth, we are protected by the atmosphere and the magnetic field. In interstellar space, there is no protection. Cosmic rays pass through spacecraft walls, through equipment, through human tissue. They damage DNA, increase cancer risk, degrade electronics, cloud sensors. A journey lasting decades or centuries would expose a crew to radiation doses far beyond anything humans have experienced. You could add more shielding, but again, shielding is mass. You could try to build a magnetic field around the spacecraft, but that requires power, constantly, for the entire journey. And the longer the journey, the more likely it is that something fails, that the shielding degrades, that the field collapses, that the cosmic ray you didn't see coming tears through the hull and kills everyone on board in an instant. The galactic cosmic ray background is relentless. It does not stop. It does not vary significantly with location. Wherever you go in the galaxy, you are exposed. On a journey to Proxima Centauri lasting decades, crew members would accumulate radiation doses measured in sieverts, far beyond the threshold for acute radiation sickness. The risk of cancer would approach certainty. The risk of neurological damage, cardiovascular disease, cataracts, immune system failure, all of these increase with cumulative radiation exposure. You cannot shield against all of it. The best you can do is reduce the dose, and even with meters of shielding, you are only buying time. This is the environment. It is not hostile in the sense of intention. It is simply indifferent. It does not care whether you survive. It does not bend its rules to accommodate biology. It is what it is, and it is lethal. And then there are the humans themselves. A journey to another star, even the nearest one, would take decades at minimum. More realistically, it would take centuries. Human beings do not live for centuries. Human beings live for 70, 80, maybe 100 years if they are lucky. A crew that leaves Earth would die long before arrival. Their children would grow up on the ship. Their grandchildren would live their entire lives in transit. Their great-great-great-grandchildren would be the ones to arrive, if the ship survives that long, if the systems don't fail, if the society on board doesn't collapse under the weight of isolation and confinement. This is the generation ship concept, the idea that you send not astronauts, but a civilization, a self-sustaining population capable of reproduction, education, culture, governance, across the span of a journey that outlasts nations. It sounds poetic. It sounds like science fiction. And it is science fiction because the engineering challenges are insurmountable. A generation ship would need to carry not just food and water, but farms. Not just air, but an ecosystem capable of recycling waste into oxygen. Not just people, but genetic diversity sufficient to avoid inbreeding over dozens of generations. The minimum viable population for a multi-generational journey is debated, but estimates range from several hundred to several thousand individuals. Below this threshold, genetic drift and inbreeding depression increase the risk of hereditary diseases, reduced fertility, and population collapse. You would need a breeding program, careful management of genetic diversity, tracking lineages across generations to avoid consanguinity. You would need to solve not just engineering problems, but biological ones, social ones, ethical ones. The ship would need schools, hospitals, governance structures, conflict resolution. It would need to maintain technology across centuries, preserve knowledge across generations who never asked to be on the ship, who were born into the journey and will die in transit without ever reaching the destination. How do you pass down the skills to operate a fusion reactor when no one alive has ever seen Earth? When the purpose of the mission is an abstract idea taught in classrooms? When the destination is a star you can barely see against the black? And it would need to function perfectly. A single catastrophic failure, a hull breach, a reactor meltdown, a disease outbreak, a civil war would mean extinction. There is no rescue in interstellar space. There is no turning back. The ship is a closed system, utterly alone, and if it fails, everyone dies. There are no spare parts except what you bring. There is no resupply. There is no backup. You must anticipate every failure mode, design redundancy into every critical system, and hope that nothing unexpected happens. But unexpected things always happen. Seals degrade, bearings wear out, electronics fail, materials fatigue, micrometeorites puncture hulls, cosmic rays corrupt computer memory. Systems that were designed to last a century might fail after 50 years, or 30, or 10. And when they fail, you must repair them using only the tools and materials on board. The psychological dimension adds another layer of impossibility. Human psychology adds another layer of impossibility. We are not evolved for confinement. We are not designed to live our entire lives in a metal tube, recycling the same air, seeing the same faces, knowing we will never stand on solid ground. Studies of isolated populations, submarines, Antarctic stations, long-duration space missions show that humans struggle with confinement even over months. Depression, anxiety, interpersonal conflict all escalate in enclosed environments. Now extend that to lifetimes, to generations, to a population that knows their children's children's children will still be trapped in the same ship, traveling through darkness toward a destination none of them will ever see. The psychological toll is not speculation. It is predictable. And it is unsolvable. You cannot engineer away claustrophobia. You cannot design out the human need for horizon, for weather, for Earth. Some generation ship proposals include virtual reality, simulated environments where crew members can experience forests and oceans and open skies. But virtual reality is not reality. The brain knows the difference. The body knows. You can simulate the visual experience of standing on a beach, but you cannot simulate the feeling of wind, the smell of salt, the sound of waves that extends beyond the speakers, the knowledge that the horizon continues beyond what you can see. Virtual reality is a band-aid on a wound that will not heal. And then there is the problem of purpose. The first generation volunteers. They understand the mission. They believe in it. They are willing to sacrifice their lives for a goal larger than themselves. But their children did not volunteer. Their children were born into the mission, given no choice, and told that their entire existence serves a purpose they will never see fulfilled. How long before resentment builds? How long before someone asks why they should continue? Why they should maintain systems for a destination generations away when they could turn the ship around, or alter course to a closer star, or simply stop and build a life in the emptiness between. A generation ship is not just a spacecraft, it is a society, and societies fracture. They experience conflict, power struggles, ideological splits. On Earth, dissatisfied populations can leave, can migrate, can start new communities. On a generation ship, there is nowhere to go. Dissent has no outlet. Conflict has no resolution except dominance or destruction. There is a darker possibility that the mission succeeds, that the ship arrives at its destination after centuries in transit, and the descendants of the original crew emerge to find a world that is uninhabitable. That Proxima Centauri b, the planet they travelled light years to reach, is a barren rock battered by stellar flares, with no atmosphere, no water, no resources. That the data was wrong, that the spectroscopic analysis misled them, that what appeared habitable from a distance is, up close, a graveyard. And there is no going back. The ship's fuel is exhausted, the systems are failing, the population is aging. They are stranded at a dead world, 4 light years from home, with no hope of rescue and no ability to leave. This is not a hypothetical tragedy. This is a predictable outcome of interstellar exploration. We cannot know what a planet is truly like until we arrive. Spectroscopy can tell us about atmospheric composition, surface temperature, the presence of water vapor. It cannot tell us about surface conditions, magnetic fields, geological activity, whether the planet is tectonically stable or geologically dead. It cannot tell us if the water is accessible or locked in ice. It cannot tell us if the atmosphere is breathable or toxic. And by the time we know, it is too late to change course. Let's talk about cryosleep, the idea that you freeze the crew, put them into suspended animation, and wake them up at the destination. It eliminates the generation problem. It solves the psychological issue. It sounds elegant. It is also fantasy. Cryopreservation works to a degree for cells and tissues. Small samples can be frozen and revived. Embryos can be frozen and later implanted. But freezing a human body, a fully formed adult with a functioning brain and complex organ systems, is an entirely different problem. When water freezes, it expands. Ice crystals form, tearing through cell membranes, rupturing blood vessels, destroying tissue. The damage is not repairable with current medicine. You cannot thaw a frozen human and expect them to wake up. They are dead. Vitrification, a process that prevents ice crystal formation by using cryoprotectants, has shown promise in smaller organisms. Certain nematodes, tardigrades, and frogs can survive freezing through natural adaptations. But these are millimeter-scale creatures with simple biology. Scaling vitrification to a human body, with meters of tissue, with a brain containing billions of interconnected neurons, is a problem no one has solved. The cryoprotectants must penetrate every cell uniformly without causing toxicity. The cooling must be rapid enough to vitrify but controlled enough to avoid thermal shock. The storage must be stable for decades or centuries, with no fluctuations in temperature, no mechanical vibrations, no exposure to radiation that could disrupt the molecular structure. Even if you could vitrify a body, you would still need to revive it. You would need to warm it uniformly, avoid thermal shock, reverse any molecular damage, restore blood flow, restart the heart, wake the brain. And you would need to do this after decades or centuries of storage, with equipment that has been dormant just as long, in an environment of radiation and micrometeorite impacts and system decay. The revival process would need to be automated, controlled by computers and robots, because there is no one awake to perform it manually. And if the process fails, if the warming is too fast or too slow, if the cryoprotectants cause toxicity, if the brain does not wake up properly, the person dies. You have travelled light years to a new star, and your crew is a collection of corpses preserved in ice. Cryosleep is not a technology, it is a hope. And building a spacecraft around a hope is not engineering. What about artificial intelligence? Send robots instead. Send machines that do not need food, water, or psychological support. Build self-replicating probes that can repair themselves, adapt to new environments, transmit data back to Earth. This is more feasible than sending humans. It is still not feasible. A probe traveling to another star would take decades or centuries to arrive. In that time, the civilization that launched it will have changed. Technology will have advanced. The priorities that justified the mission may no longer exist. And when the probe finally arrives, when it begins transmitting data back to Earth, the signal will take years to return. A message sent from Proxima Centauri takes 4.24 years to reach us, traveling at the speed of light. A conversation is impossible. A command to adjust course, to investigate a particular phenomenon, to respond to an unexpected discovery, all of these require waiting nearly a decade for a round-trip message. By the time the probe receives new instructions, the opportunity may have passed. The environment may have changed. The data may already be obsolete, and this assumes the probe survives. Machines fail. Electronics degrade. Cosmic rays corrupt memory. Micrometeorites puncture instruments. Power sources decay. A probe designed to function for a century is subject to a century of entropy, with no maintenance, no repairs, no replacements. It is alone. And if it fails, we lose it. We lose everything it carried, everything it was meant to discover, and we will not know for years that it stopped transmitting. The signal simply stops arriving, and we are left to wonder whether the probe failed, or whether it discovered something so dangerous it was destroyed, or whether the data is still being transmitted but we can no longer receive it. Self-replicating probes, the von Neumann concept, add another layer of complexity. The idea is to send a probe that, upon arriving at a destination, uses local resources to build copies of itself, which then launch toward new destinations, exponentially spreading across the galaxy. It is an elegant solution to the problem of scale. A single probe becomes 2, then 4, then 8, eventually numbering in the billions, exploring every star system in the galaxy. But self-replication is not simple. The probe must be able to mine asteroids, refine metals, manufacture electronics, assemble complex machinery, all without human oversight. It must carry the knowledge to build itself, encoded in software that must function perfectly across generations of copies. Any error in the replication process, any mutation in the software, propagates forward, potentially creating probes that malfunction, or worse, that replicate uncontrollably, consuming resources without purpose. And there is the risk of contamination. A self-replicating probe that lands on a planet with primitive life could destroy that life, inadvertently or through malfunction. It could consume the planet's resources, turning it into more copies of itself, an exponential disaster that spreads faster than we could stop it. The ethical implications are severe. Do we have the right to send machines that could sterilize other worlds? Do we have the right to impose our presence on environments we do not understand? These are not engineering questions. They are moral ones, and they do not have easy answers. The fantasy of interstellar travel relies on technologies that do not exist and cannot exist within the boundaries of physics as we understand it. Warp drives, the concept of bending space-time to move faster than light without actually moving faster than light, require exotic matter with negative mass energy. We have never observed negative mass. We do not know if it is possible. Alcubierre's original warp drive metric, a mathematical framework showing how space-time could theoretically be warped, requires more energy than exists in the observable universe. Subsequent refinements have reduced the energy requirements, but only down to scales equivalent to Jupiter's mass converted entirely into energy. This is not engineering. This is mathematics applied to ideas that may be fundamentally impossible. The Alcubierre metric describes a bubble of space-time that contracts space in front of a spacecraft and expands space behind it, allowing the craft to effectively move faster than light without violating relativity. Inside the bubble, space-time is flat, and the spacecraft experiences no acceleration. From an outside perspective, the spacecraft appears to move faster than light. It is a beautiful concept. It is also likely impossible for reasons that go beyond energy. First, the exotic matter required to create the bubble must have negative energy density, a property that violates all known physics. The Casimir effect, a quantum phenomenon that produces a small attractive force between parallel plates in a vacuum, is sometimes cited as evidence that negative energy exists. But the Casimir effect does not produce negative energy in the sense required by the warp drive. It produces a region of lower than average vacuum energy, not energy that is less than zero. True negative energy, energy that could curve space-time in the way the Alcubierre metric requires, has never been observed and may be forbidden by quantum field theory. Second, even if exotic matter exists, even if you could produce it in sufficient quantities, the creation of a warp bubble would likely produce catastrophic side effects. The intense curvature of space-time at the edges of the bubble would generate Hawking radiation, high-energy particles created by quantum effects near event horizons. The radiation would be intense enough to destroy anything inside the bubble, including the spacecraft. And when the bubble collapses, when you arrive at your destination and deactivate the warp drive, the energy stored in the distorted space-time would be released in a burst that could sterilize the surrounding region. Third, you cannot steer a warp bubble. Once created, the bubble moves in a straight line at a speed determined by the energy you put into it. You cannot change course. You cannot stop. You cannot accelerate or decelerate without collapsing the bubble and creating a new one. This means you must aim perfectly from the start, and if your destination moves, if the star you're traveling to has drifted in its orbit, if your trajectory is off by even a fraction of a degree, you will miss. And at faster than light speeds, a small angular error translates to vast distances. You could overshoot your target by light years and not realize it until you collapse the bubble and look around. Wormholes, shortcuts through space-time connecting distant regions, require similar exotic matter to remain stable. Naturally occurring wormholes, if they exist, would collapse faster than light could pass through them. Artificial wormholes would need to be held open by forces we cannot generate and materials we do not have. Even if you could create a traversable wormhole, you would still need to position it. You would need to move one end to your destination, which requires traveling there in the first place. The wormhole does not eliminate the journey, it only defers it. And there are causality problems. A wormhole connecting 2 points in space also connects 2 points in time. Depending on the relative motion of the wormhole mouths, it may be possible to travel backward in time, creating paradoxes, closed time-like curves, situations where cause and effect break down. Most physicists believe the universe has mechanisms that prevent such paradoxes, that quantum effects or unknown laws conspire to make time travel impossible. But we do not know, and gambling on wormholes when we do not understand the consequences is not a plan. These ideas are mathematically interesting. They are consistent with general relativity in the same way that traveling backward in time is consistent with relativity. Consistency with known physics is not the same as feasibility. Relativity allows for many things that do not happen. It allows for closed time-like curves, for regions of space-time where you could meet your own past. But we do not build time machines because the conditions required do not exist in nature and cannot be created by technology. The same is true for warp drives and wormholes. They are not technologies waiting to be invented. They are speculative ideas that may be forbidden by deeper laws we do not yet understand. And even if we solve propulsion, even if we solve energy, even if we somehow build a ship capable of reaching another star, we must confront the question, why? What is on the other side that justifies the cost, the risk, the generations of human life spent in transit? Proxima Centauri has a planet, Proxima Centauri b, orbiting in the star's habitable zone. It is 1.17 times the mass of Earth. It receives similar levels of radiation from its star. On paper, it could have liquid water. It could, hypothetically, support life. But Proxima Centauri is a red dwarf, a star that flares violently, emitting bursts of radiation that would sterilize the surface of any nearby planet. The planet is tidally locked, one side always facing the star, one side in eternal darkness. The temperature gradient between day and night would drive winds at hundreds of miles per hour. The magnetic field, if it exists, would be battered by stellar flares. And even if the planet is habitable, even if there is water and atmosphere and no immediate lethal conditions, it is 4.24 light-years away. A round-trip message takes 8.5 years. A journey takes lifetimes. A mistake means death. You do not send humans to Proxima Centauri to explore. You send them to die there, because there is no return. There is no rescue. There is no backup plan. If the planet is uninhabitable, if the environment is toxic, if the systems fail, the crew dies. And Earth will not know for years. This is not colonization, it is exile. And Proxima Centauri is the closest star. The next habitable world might be 10 light-years away, 20, 50. The odds that a nearby star has an Earth-like planet with breathable atmosphere, with stable climate, with resources humans can use, are low. The galaxy is full of planets, but most are gas giants, or icy moons, or scorched rocks orbiting too close to their stars, or frozen wastelands too far away. The habitable zone, the region around a star where liquid water can exist, is narrow. And even within that zone, conditions vary wildly. A planet can be in the habitable zone and still be uninhabitable. Venus is in the Sun's habitable zone, and its surface is hot enough to melt lead. Finding a world that is not just habitable, but welcoming, a world where humans could thrive rather than merely survive, is vanishingly rare. And each candidate is light-years apart. You cannot explore the galaxy the way explorers charted Earth. You cannot sail from star to star, testing new shores, moving on if the conditions are poor. Every journey is a multi-generational commitment to a destination chosen based on incomplete data, on spectra analysed from light-years away, on guesses about what might be there. And if you are wrong, if the data misled you, if the planet is not what you hoped, you cannot simply leave. You are there, you are stuck, because the energy required to leave is the same as the energy required to arrive, and you have already spent it getting there. Let's zoom out further. Let's imagine generously that humanity solves all of these problems, that we build ships capable of reaching 10% of light speed, that we develop closed-loop life support systems that last for centuries, that we send missions to the nearest stars, and some of them succeed, that we establish outposts on a handful of exoplanets within 20 light-years of Earth. We have left the solar system. We have become an interstellar species, and we are still trapped. The Milky Way galaxy contains 100 to 400 billion stars. It is 100,000 light-years in diameter. The galactic disk, where most stars reside, is about 1,000 light-years thick. The stars are not uniformly distributed. They cluster in spiral arms, in dense regions near the galactic center, in sparse regions toward the outer edge. The average distance between stars in our neighborhood is about 4 to 5 light years. In denser regions, it might be 2 light years. In sparse regions, it might be 10 or 20. At 10% of light speed, crossing the galaxy would take 1 million years. The stars we could reach within a human lifetime, even traveling at relativistic speeds, number in the dozens. The stars we could reach within a millennium number in the thousands. This is not expansion. This is a slight widening of our cage. Even if we colonize 1,000 star systems, we would occupy less than 1/1,000,000th of the galaxy. We would be scattered across a region 100 light-years across, a tiny bubble in a disk that stretches 100,000 light-years from edge to edge. The rest of the galaxy would remain as distant, as unreachable as it is now. And the distances between our colonies would be measured in decades of travel time, meaning they would evolve independently, diverge culturally and technologically, potentially become isolated from each other as resources dwindle and the motivation to maintain contact fades. Human civilization on Earth has existed for perhaps 10,000 years, depending on how you define civilization. In that time, we have split into thousands of cultures, languages, nations. We have fought wars over territory, resources, ideology. We have built and destroyed empires. Now imagine that process stretched across light years, across star systems where communication takes years and travel takes lifetimes. The idea that we would remain a unified species, that the colonies would share common purpose and identity, is not realistic. They would become separate civilizations, as alien to each other as ancient Mesopotamia is to modern America, connected only by the historical fact of common origin. The local group, the collection of galaxies gravitationally bound to the Milky Way, includes Andromeda, 2.5 million light-years away. At the speed of light, a journey to Andromeda takes 2.5 million years. At 10% of light speed, it takes 25 million years. Civilizations do not last 25 million years. Species do not last 25 million years. Homo sapiens has existed for 300,000 years. Homo erectus, our evolutionary ancestor, existed for about 2 million years before going extinct. The dinosaurs as a group lasted 165 million years, but individual species within that group lasted only a few million years each. The idea that we could sustain a continuous technological society for 25 million years, long enough to send a ship to Andromeda and receive a signal back, is beyond optimism. It is delusion. And beyond the local group, the universe is expanding. Dark energy, the mysterious force accelerating the expansion of space, is pulling distant galaxies away from us faster than light can travel. The expansion is not uniform. Nearby galaxies, those within our gravitational group, are not receding. But beyond a certain distance, the recession velocity exceeds the speed of light. This does not violate relativity, because the galaxies themselves are not moving through space faster than light. Space itself is expanding between us and them, carrying them away. There are galaxies we can see, whose light has reached us, that we will never visit. Not because we lack the technology, but because the space between us and them is growing faster than we could ever cross it. Those galaxies are not unreachable in the sense of being far away. They are unreachable in the sense of being fundamentally inaccessible, beyond an event. Horizon created not by gravity, but by expansion. The expansion of the universe has placed them beyond a boundary we cannot cross, no matter how fast we travel, no matter how long we wait. This is the cosmic scale. Leaving the solar system, reaching a nearby star, establishing a foothold on an exoplanet, these achievements, if they ever happen, are cosmically insignificant. They do not make us a spacefaring species. They make us a species that has crawled a few inches farther from home in a universe measured in billions of light years. The observable universe is 93 billion light years in diameter. It contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Most of those stars have planets. And we will never see them. We will never visit them. We will never know what is there. Not because we lack curiosity, but because the universe is too large and we are too slow and the laws of physics do not care. There is a concept in cosmology called the cosmological horizon, the boundary beyond which light has not had time to reach us since the beginning of the universe. Everything beyond this horizon is invisible, not because it does not exist, but because the universe has not existed long enough for its light to cross the distance. As the universe continues to expand, this horizon grows, but not fast enough to keep pace with expansion. Galaxies that are currently visible will eventually cross beyond the horizon and disappear, their light redshifted into invisibility, their distance growing faster than their light can reach us. In trillions of years, distant observers in those galaxies will look out into space and see nothing. No other galaxies, no cosmic microwave background, no evidence that the universe is anything other than their own galaxy surrounded by infinite emptiness. They will be alone, not because they are, but because the expansion of space has hidden everything else from view. They will develop cosmology, and they will conclude, based on all available evidence, that the universe consists of a single galaxy. They will be wrong, but they will have no way to know. We are living in a temporary window of cosmic history where the universe is old enough to have formed structure, galaxies and stars and planets, but young enough that we can still see other galaxies, still infer the history of the Big Bang, still understand the large-scale structure of reality. This window will close, and when it does, the civilizations that come after, if any do, will look out and see a smaller universe than we do. They will be more isolated, more confined, more alone. Humanity is trapped not just by distance, but by time, by the era we happen to exist in, by the fact that we emerged on a planet orbiting a star at a time when interstellar space is crossable in principle, but not in practice. We can see the stars. We can measure their distances. We can dream of reaching them, but we cannot go. And the longer we wait, the harder it becomes, because the universe is not static. It is expanding, changing, evolving in ways that make the future less accessible, not more. There is a subtle tragedy in this. We are intelligent enough to understand the scale of the universe. We are curious enough to want to explore it. We are technologically advanced enough to send machines to the edge of our solar system, to land robots on other worlds, to detect planets around distant stars. And we are physically incapable of going there. We are like a species born in a prison that has windows but no doors. We can see outside. We can study what is out there, but we cannot leave. Some have argued that this is fine, that humanity does not need to leave the solar system to thrive, that our future lies in building megastructures around our own sun, in terraforming Mars and Venus, in colonizing the asteroid belt and the moons of Jupiter and Saturn, in constructing habitats in space where billions or trillions of people could live. This is optimistic. It is also still confinement. A larger cage is still a cage. And it assumes the solar system is safe, that the sun will not flare unexpectedly, that a rogue planet will not pass through and destabilize the orbits, that a nearby supernova will not bathe the inner solar system in lethal radiation. These events are rare, but they are not impossible. The sun is a middle-aged star, stable for now, but stellar activity is unpredictable. Supernovae occur in the galaxy at a rate of about 1 every 50 years. Most are far enough away that they pose no threat. But a supernova within 30 light-years would bombard Earth with gamma rays, stripping the ozone layer, sterilizing the surface. We have evidence that such events have occurred in Earth's history, mass extinctions correlated with nearby supernovae. It could happen again. The Sun is 4.6 billion years old. It has another 5 billion years of stable life before it exhausts its hydrogen and begins expanding into a red giant, a process that will destroy Earth and Mars and possibly Venus. 5 billion years is a long time. It is longer than life has existed on Earth, but it is not infinite, and when the Sun dies, everything in the solar system dies with it. Unless we leave, but we will not leave, because we cannot, because the distance to the next star is measured in light years, and we move in kilometers per second, because the energy required is beyond what we can generate, because the time required is beyond what humans can endure, because the universe is vast and indifferent and does not provide shortcuts for species that dream of exploring it. We are alone, not because there is no other life in the universe, but because the distances between stars make contact functionally impossible. If there are other civilizations out there, they face the same problem. They see the same stars, measure the same distances, confront the same physics. They are as trapped as we are. And if they are more advanced, if they have survived for millions of years longer than we have, they still cannot escape. Because the problem is not technology, the problem is the universe itself. There is a term in the Fermi paradox literature called the Great Filter, a hypothetical barrier that prevents civilizations from reaching interstellar status. Some argue the filter is behind us, that the emergence of intelligent life is so rare that we are alone in the galaxy. Others argue the filter is ahead, that something, whether extinction by war or environmental collapse or some other catastrophe, destroys civilizations before they can leave their homeworlds. But there is a third possibility. The filter is not an event. It is distance. It is the structure of space-time itself. It is the fact that stars are light years apart and light years are too far. Civilizations do not spread across the galaxy because they cannot, not because they destroy themselves, not because they lack ambition, but because the universe has made interstellar travel effectively impossible. The speed of light is too slow, the distances are too great, the energy requirements are too high, the timescales are too long, and no amount of technological advancement changes the fundamental equation. We have spent a century imagining a future among the stars. We have written stories about starships and galactic empires and faster-than-light travel. We have dreamed of a universe where distance is an inconvenience rather than a barrier, where humans spread across the Milky Way and beyond, where Earth is just the beginning of a story that spans the cosmos. It is a beautiful dream. It is inspiring. It has driven scientific progress and exploration and ambition. But it is a fantasy, and the longer we cling to it, the harder it becomes to accept the reality we actually face. The reality is that we are here. We are bound to this solar system. We orbit a single ordinary star in the outer reaches of an ordinary galaxy, and we will never leave. Not because we do not try, but because the universe does not allow it. The stars we see in the night sky are not destinations. They are images, fossils of light that traveled for years to reach us, and we will never travel back to their source. We are witnesses, not explorers, observers, not participants. We can study the universe, catalogue its wonders, measure its scale, understand its history, but we cannot touch it. We cannot be part of it beyond the tiny sphere of space the sun has carved out for us. And perhaps that is the final quiet truth, that humanity is not meant to be an interstellar species, that we are a local phenomenon, bound by physics to the place we evolved, confined by distance to the system that gave us life, that our future, if we have one, is measured not in light years but in astronomical units, that we will build and grow and change and eventually die here, in this solar system, under this sun, without ever knowing what lies beyond. The universe is too large. We are too small, and the distance between stars is not a challenge to overcome. It is a wall we cannot break, invisible, impassable, permanent. We are already home. We have always been home, and we will never leave.